Night has fallen, so it's good to say good evening and welcome to our final session, our plenary table. My name is David Patrician, a great honor to welcome you all here. 2 words about myself. I'm originally from the United States. I came over on a Fulbright scholarship, and life is everything that happens in between the planning. My 1 year has turned into 14 years. I work for RTL and NTV, German language studios, but I'm happy to be doing some work in my native English. We have a fantastic panel, and before we start, let's just all take a breath. It's been one heck of a week. I'm a big history buff. If we look back, Tuesday night, the United States re-elected Donald Trump to become president. As those people who are film buffs know, sometimes the sequel is not as good as the original. We shall wait and see. On Wednesday, the German cabinet reshuffled itself and the ample coalition went into a crisis mode. And then, of course, tomorrow we have a historical day, November 9th, 35 years since the Berlin Wall fell here in the city. And in between everything, we are here at the Falling Walls Science Summit. So it certainly is a very, very eventful week. We'll be talking in our session today about HPC, or as some people like to say, the supercomputers, and AI solutions, a collective and international effort. 2 or 3 quick words about this session. In the spring of 2025, Europe will mark a significant milestone with the launch of its first high-performance computer, HPC, at the Forschungszentrum Jülich. The HPC will be capable of performing over 1 quintillion calculations per second and promises to revolutionize scientific simulations and artificial intelligence. Today, we have the honor of bringing together leading HPC manufacturers, AI experts, and researchers to discuss synergies between HPC and AI, while also exploring how the powerful combination can effectively address some of the most pressing societal changes we face today, including unlocking new possibilities for breakthrough in vital areas such as climate change, energy, sustainability, and health and research. I'm going to introduce our guests. I'll say 2 or 3 words about them and then bring them here to our stage. It's a great honor. Our first guest is Richard Socher. Richard is the founder and CEO of U.com and is an advanced search engine powered by artificial intelligence. Similar to OpenAI's technology, search queries can be retrieved, results ranked, and AI technology utilized to translate them into different languages. Ladies and gentlemen, Richard Socher. Welcome. Welcome to the stage, sir. Welcome. Next up, we have John Josephakis. John is a global VP of Sales and Business and Development for HPC AI at NVIDIA, a company that I think most of us are now familiar with. And NVIDIA, of course, is a leader in artificial intelligence, computing, and global manufacturer for high-end and graphics processing units. Ladies and gentlemen, please help me welcome John Josephakis. John, welcome.
Thank you.
Good to see you, please. Then, our third member is Kohei Ito. Kohei's current role in Japan includes the executive member of the Council for Science, Technology, and Innovation, chair of the government's Quantum Technology Innovation Experts Panel, and committee member of the promotion of the High Performance Computing Infrastructure Project, and council member of Science Council of Japan. Please help me welcome Kohei Ito. Kohei, welcome. Good to see you. And finally, we have Paul Kearns. Paul is a biologist and accomplished steward of diverse scientific resources to achieve ambitious goals in energy. Paul has served as director of the U.S. Department of Energy's Argonne National Laboratory since 2017. Please help me welcome Paul Kearns. Paul. Welcome. Thank you very much. After speaking German for so many weeks, I'm realizing I have a few tongue twisters here in English, but we'll get there. We'll get there. I'll get back to it. I also wanted to take a moment to introduce Astrid Lambrecht. Unfortunately, she was supposed to be on our panel today, but she had a family member or family situation, so she couldn't join us. But Astrid Lambrecht, she's the chair of the board of directors of the Forschungszentrum Jülich. She also sends her regards. Okay, gentlemen, let us begin with our discussion. And I'd like to start with you. A few ground rules before we begin. This is also my first time here at the Falling Walls Science Summit, so I'm getting used to it. But we have about 30 minutes for our discussion. Of course, I'll ask the questions, but you are more than welcome to discuss amongst each other some of the issues. After that, I sat in on 1 or 2 of the plenary sessions, and I always saw there was a lot of questions from the Q&A. So I'm going to really try to get at least 15 minutes of Q&A time here. And then we have our final question, and then I'll say a few words tonight about our AI night. So let us begin. John, the first question.
Okay.
How is AI-based science currently influencing hardware development, and what role might it play in shaping future hardware demands compared to those of classical simulations?
Okay, very good question. Thank you. Well, AI is playing an important role in everything we do these days. However, everything starts with science. So science is where we look at NVIDIA, for example, and with a lot of our customers, we look at science to drive the technology, because the scientific problems keep getting larger and larger. And in order to solve those with AI or with classical modeling simulation, are getting to the point where you need to advance technology design. So that in itself forces us to look at new areas like memory technology, network technology, data center designs, and I keep going. But in an overview, everything is driven by the fact that scientific challenges become larger, AI is driving them to be faster, and the combination of all indeed drives innovation in hardware technology.
Yeah, when I was doing some research and talking to some of the people the last few days, I've heard often that academia and the private sector are on parallel terms, and they really should try to come back together. Is NVIDIA reaching out to the academic world to do that at all?
Actually, I've been driven by that. It's funny, I was talking with Ito-san, and I was in Japan last week, and I was at his university. Yesterday, I was actually in another country at the National University Center with the minister, talking about startups and collaborations. So yes, at NVIDIA, we are very focused in high ed, in research computing, and how we can bring industry and startups too. We need to bring the ecosystem startups together to leverage a lot of the research that's happening at a lot of the universities.
Outstanding. Okay, thank you very much. Kohei, and we all agreed we could do first name basis, just want to make clear, because in German we have Dutzen and Sitzen. And I'm David, of course. Kohei, what are the current developments in high-performance computing, HPCs, in Japan and other regions? And what advancements are expected in future computing architectures, such as your specialty, quantum or hybrid machines?
Okay. So 2011, about 13 years ago, Japan introduced a supercomputer or high-performance computer called K, which actually operated 10 petaflops per second and so on. But then, after 10 years, 2021, we also introduced a flagship high-performance computer called Fugaku. And we spent 5 or 6 years designing this Fugaku. And meanwhile, of course, you know what happened. All these machine learning emerged, and such spending of time for designing architecture and all so on is a very difficult task, because you can never predict what's coming in 5 years. And we're doing the same thing right now. We're designing the next flagship computer, Fugaku Next. It has to be flexible enough that it can actually incorporate whatever comes in the next invention, which is a very hard task to do. Fugaku current flagship computer is doing very well in the sense that it was designed flexible enough that it was, it's doing very well with the AI adaptation. But still, John and I were talking, before the session that, how can anyone design computer for 5 years to come is a big question.
Yeah.
So that's where we are. But quantum in the long run will definitely come into play because of this, saturation of so-called Moore's law for the semiconductors, because the advancement of the supercomputer or high-performance computer has been depending on advancement in semiconductors. But now it's saturating, so you mentioned memory and all these technology has to come together.
Yeah.
And quantum is one key, probably, element for advancement of the, not only speed, also for the reduction of the power usage.
And let me ask you one follow-up question. I'm living here in Germany, of course, for many years. And Germany, there's no secret, has been very slow to digitalization. And many people say during the corona, the COVID pandemic, that was really the kick in the butt that got the government going to a much faster term. I'm curious, Japan and Asia in general, do you find that in the Japanese government, people are very proactive when it comes to HPCs, to AI, or is it hitting against the wall?
I think Japan and Germany probably share the same challenges.
Oh, okay.
Yes.
Okay.
So it's quite bureaucratic sometimes. And also, planning is something that they really really want to spend on. But still, now we have to do everything more proactively, as you pointed out. So we have to adjust ourselves.
Yeah, okay.
The driver will be the private sector too. It's very hard for the country to say, oh, we're going to plan to have high-performance computing.
Yeah, excellent. And Richard, thank you for jumping in because I wanted to ask you, first of all, can you just tell us 2 or 3 sentences about U.com before we begin, please?
Happy to, yeah. U.com is a productivity engine, which is sort of the next level from a search or an answering engine. We realize that the problem isn't anymore that you have access to information. The problem is that there's too much information. And so we have to help people summarize it and then help people become more productive. Ultimately, a lot of the large language models that are driving what we see with ChatGPT are essentially just neural sequence models. And other types of sequences are proteins, which is really exciting, and research I've done in 2020 where we actually created the largest language model for proteins. But these sequence models can also include actions. And so what we're seeing now with our customers is that they're building agents that will just map entire workflows, things that would have taken 5, 10 hours for them to do, they can do in 5 minutes. And yes, there's a lot of language and knowledge involved too, but it's also steps in the workflow. And so that's why we're calling ourselves a productivity engine now.
Interesting. Can I ask you, I'm sure you have demographics. Is there 1 or 2 countries that you have a lot of customers from? I mean, where are the...
They actually happen to be the US and Germany. So.
US and Germany. Okay, fair enough. Very good. I wanted to lead off with the question for you, Richard. How does the AI system U.com, your company, leverage its potential applications in science? And what are its strengths in trust and, very important, in transparency?
That's right, yeah. So it's actually with LLMs and thanks to a lot of APIs and also open source software, it's very easy these days to build a prototype. And you're just like, look, it works. I asked it a question and it gives me an answer. But then you actually try to really scale it up and do it accurately millions of times a day, you realize there's actually a lot more to it. So LLMs will give you an accurate answer maybe 60% of the time, and you don't know which of the 60% it is. And so we've pioneered since 2022 to connect LLMs to a search engine stack. And the search engine stack is kind of really, really crucial because if you give garbage into the prompt of an LM, it'll just mostly give you garbage back out. It's very hard to recover from a bad search infrastructure that sits below the LLMs. And so we've been focusing on that, and that led us to also focusing on citation accuracy. So when you have a search index and you bring the right facts to it, then you can actually also have citations for where each of the facts come from that the LLM gives you in its summary. And we've seen some of the competition kind of fake the citations. They just sprinkle random numbered links behind sentences that have nothing to do with one another. So there's a lot of like quick prototype building, but not really accurate answers. And so what we're seeing now is customers like the Institute of Advanced Study in Princeton, where Einstein Oppenheimer worked. They just became a customer a few weeks ago of U.com. We see Maryville University and other German universities working with us and become customers. Basically, organizations that care about trust and accuracy, and also the citations, like DPA, the German press agency. Those are organizations that care about it and hence end up using U.com.
Got it. It's very interesting. In my field, we're dealing with fake news and deepfakes, and you're dealing with fake citations. So it seems like everywhere we have to deal with what is the truth and where's the sources coming from. Paul, I wanted to turn to you. I wanted to ask you, what are the specific strengths of the Aurora exascale computer in addressing current high-performance computers, HPCs, and AI applications for tackling grand challenges? And of course, Aurora is one of the world's first exascale supercomputers. I have to admit, I looked that up. Exascale, for anyone that's not aware of that, it's a type of ultra-powerful supercomputing with systems performing billions of computations per second, utilizing an infrastructure of CPUs and GPUs to process and analyze data. Really fascinating stuff.
Yeah. Wow. Thank you, David, really, for the question. Yes, I like to think of Aurora really as it's built for AI from the beginning. That was designed with that purpose in mind, and fortunately, the scientists at Argonne, I think, had the foresight to really value artificial intelligence, recognizing how quickly the field was evolving and really the great need that would come. I like to think of it in terms of scale. A billion calculations a second is what it's able to do. It's really 60,000 GPUs. Unfortunately, they're not NVIDIA. They're Intel GPUs, a competitor, if you will, but really it's in the process of being, we're completing the commissioning. It's going to be go through the acceptance testing here in the next month, and we'll make it available to users across, not only at Argonne, but across the US and across the world. It is one of the Department of Energy's National Scientific User Facilities, so it's free to use. People can come and offer their thoughts on how to put it to good use, and it'll be evaluated, peer reviewed, and then it'll be, a decision will be made, and there'll be granted time if it indeed is worthwhile. To do the science, or it's appropriate to do the science at that scale, so that's important. It's really across all fields of science, really in terms of its potential value, and everything from cosmology all the way to thinking about identification of new materials that might develop the improved efficiency in terms of energy storage to enable the clean energy transition, as an example. So many applications. I think one of my favorites to imagine really is understanding the brain and the connections within the brain. Really a big challenge in terms of where we're at today and where we would like to be.
Yeah, and you mentioned clean energy transition. I know we just had the elections. The results are out less than 48 hours, with Donald Trump being the next president again. But just one or two sentences. Do you think that will have an impact as far as your work dealing with the HPCs?
It's a little early to tell,
Sure.
really, what the outcome's going to be. Really, it's certainly a topic that's been in active discussion, but it really gets down to the leaders that are selected to serve in the government and the policies, priorities they bring with them. So that's really critical. I think it's recognized broadly there's great value, really, in terms of economic opportunity that comes with the transition to clean energy technology. So I'm hopeful that prevails.
Excellent. A very diplomatic answer. We'd love you in Washington. Excellent.
If I may add
Please,
something.
go ahead.
Because one of the energies you mentioned, the clean energy. So one of the projects we're collaborating actually with the Argonne National Labs is batteries. Battery technology. And Argonne is one of the leaders worldwide in battery technology development. So even though their big machine doesn't happen to have NVIDIA, we continuously collaborate on a scientific, they do have an NVIDIA machine too, but we do collaborate on different areas looking at future technologies with Argonne, and actually battery technology is one of the areas that clean energy where Argonne is leading, and we are collaborating as a private entity, as Richard was saying, with the university, with the professors at Argonne.
Yeah, thank you.
Excellent, very good, good synergy. John, I wanted to ask you a follow-up question here. What are the costs and performance metrics and energy efficiency considerations involved in the co-development of hardware between science? For example, we talked about the Forschungszentrum Jülich and industry, NVIDIA. I come back to it because it's something I really heard so often during my talks.
Yeah, so everything we do, we think about energy. So when we look at every product we bring to market, we don't look at just the components, but we look at system level and we benchmark according to scientific results. So we don't look at a chip and say, oh, this chip is at this performance level, but we look at the system, how all the components come together. We're talking with Richard earlier. It's compute, it's network, it's storage, it's software. So how does it all come together to provide you a solution with the best TCO, total cost of ownership? Best solution based on the power use and so forth. And that is not just what we develop for today, but we are also looking at the futures. We also collaborate with a lot of companies that are building the actual data centers, designing them with digital twins and looking forward on how does everything come together. We work with companies that have ISV codes and how those codes are going to run effectively and efficiently on future systems. So that all comes together for energy.
Great, thank you very much. Anyone else on this topic?
It'll be really exciting. Right now, if you look at the flops the human brain has versus the flops we can get out of GPUs, like there's still so much more research that we can do to drive down the marginal cost of intelligence further and further. And I'm really excited about that research.
Excellent. It all comes down to the money as well. Kohei, a question for you again. What is the current and future role of AI as a driving force in scientific computing, in your opinion?
I've been on the committee for high-performance computing in Japan, and I've been really pushing the importance of finding or making scientific discoveries using computer as a tool. And as far as I'm concerned, 2021 Nobel Prize in Physics, Toshiro Manabe, the Princeton Advanced Study, that was the first time that some Nobel Prize was given to calculational results. He showed that the CO2, carbon dioxide emission, leads to global warming. And of course, before him, many Nobel prizes were given to methodology of calculation, but for the results of calculation, 2021, as far as I'm concerned, was the first time. And this year, of course, Nobel Prize in chemistry went to AlphaFold, Google DeepMind. So I think what is important is to use high-performance computer or computer for scientific discovery, and that's what exactly Argonne National Lab is also pushing for. And for this, I think we really need a combination of all sorts of computer, like not only AI but also quantum computers and so on, to lead us to the discovery that will actually for the betterment of society. So that's I think that the HPC as a package is a tool for scientific discovery and for the betterment of the society, I think.
Excellent. And you mentioned Argonne. Let me turn to you, Paul. In your opinion, what AI expertise and models are essential for energy research at Argonne?
Yeah, I want to really kind of take it perhaps a level up in terms of my response and really think about 4 efforts that are underway, not only at Argonne, but I would say across the National Laboratory Complex and perhaps other institutions as well, but really data, really curating the data we have. The Department of Energy has really probably one of the world's largest scientific workforces and a lot of data generated over the last 70 years associated with that. How much of that is useful and to really train a large language model is a good question, right? And how do we access that information is a key component as well. We also need to think about the hardware, and it's great to have John here, and also think about the facilities required to really drive what we're doing in terms of our artificial intelligence and application in the energy space. And so energy consumption, we've already touched on a bit, a key area of research across the National Laboratory Complex, for sure. The third one is the development of the large language models, certainly driven really by that curiosity in science and engineering. And then the fourth area is really the applications. And that's when you get down to the specifics in terms of looking at energy technologies. How do we speed the development? How do we move more quickly in terms of moving them from the laboratory to deployment, and actually doing that at scale is the big challenge. So a lot of effort underway. We see many different applications, everything from, as I said earlier, looking at the materials that enable those technologies to perhaps speeding the permitting associated with those technologies, or perhaps helping us build a more efficient, interoperable electrical grid is another great example, big question mark in the United States. And so great applications, great opportunities here.
Yeah, excellent. Anyone want to add to that?
Maybe one thing to chime in that was really fun, and full disclosure, I invested in this company called Atmo. They do weather predictions, and they sell national weather forecasting services to new countries. And because, I think, correct me if I'm wrong here, but up until recently, and maybe still now, most of the high-performance computing power goes into weather prediction. Not yet AI, right? I think it's probably changing these days. But really, countries like Uganda or the Philippines couldn't afford to have a massive supercomputer and have their own weather prediction services, which meant that they would not be as well set up for the changes in climate and crazy weather events. And with this one little company, they're able to have their own weather services with the hardware, which is NVIDIA's, and then AI replacing the very expensive simulations and approximating them with neural networks. And that's a really beautiful combination of HPC and AI for climate change and for science.
I see John nodding. I know you all have many, many projects. Are you familiar with that one there? Have you heard about that?
Yes, and we also have an internal project called Earth 2. Actually, Jensen was here in Berlin about a year and a half ago, part of the EVE project. So we are very involved in a lot of the weather and climate evolution of AI in weather and climate. We're collaborating with some of the large centers like ECMWF, the European Center for Medium Weather Forecasting, and others.
Yeah.
So that's a very important area. And again, extreme weather phenomena is something that we really pay attention, and we have a couple of products on the software side that we're collaborating with many companies. Yep.
Yeah, I would jump in here
Please.
as well, and also, sorry, speak to the importance of really helping the decision makers, whether it be at the community level or the federal level or even within industry, really understand climate and the fact that it is changing, and also be able to anticipate really what that means and really think about adaptation over time and prepare for those extreme weather events effectively. And so this is an area that Argonne's been working in terms of downscaling climate information and weather data so that it becomes a neighborhood scale, basically, and people see it firsthand in terms of impact, in terms of how we visualize that information for them and can make decisions. So really based upon that.
Right.
So as far as I understood, the beauty of the AI weather prediction is that you can actually make models for different component of weather. So wind, lightning.
Wow.
Rain, all these different parts can be actually modeled separately.
And you can incorporate the landscape even.
Right.
Really cool.
Right. And then with all these, combination, and you can even tailor-made your needs depending on what you want. So I think that's that kind of thing is very fascinating.
Yeah. Yep. Yeah, interesting. Very good. Thank you, gentlemen. Richard, a question to you, and also a reminder to our audience, in about, I'd say, Pi mal Daumen auf Deutsch, in about 5 minutes, we are going to open up for Q&As. So if you want to start thinking about some questions, we'll have someone with a microphone come, we'll do a brief introduction, and then we'll have a discussion, Q&A round with our panels here. Just 1 or 2 more questions. Richard, what are the current challenges and opportunities for AI model developers, and who stands a chance to succeed under what conditions, in your opinion?
All right.
I know.
Try to squeeze that from 10 hours to 2 minutes. I think the biggest challenge right now is that the cost is extremely high if you wanted to build a foundational model. A lot of countries, certainly companies, struggle with that. You can criticize Facebook Meta on a lot of levels if you wanted to, but what they're doing to open sourcing these foundational models has been incredible for humanity as a whole. It's really that big, and it's hard to understate that. Like, now that you can have a frontier model with Llama 3 and 3.1 from Facebook Meta, you can then fine-tune it, and that actually took a major challenge away. And once Llama 4 comes out, I think it'll actually be a challenge to the large model providers. We hear Sam Altman talk about how their next LLMs that will cost maybe hundreds of millions of dollars to train will be at the level of a PhD student, which is incredible, and it's amazing and true for a lot of different tasks. But the corollary here is that most jobs don't require a PhD. And so if you have Llama 4 that will come out, you'll actually be able to do a lot of things in the economy, a lot of intellectual labor with these models. And then if you fine-tune them, which will cost actually a lot less, and can be done by many more organizations, then I think that will actually be one of the biggest challenges will disappear. And that will also allow, and is currently like the Llama 3 models, allow researchers to study these frontier models, which actually I think would reduce the challenges. I think challenges will always remain, like, any domain that we can simulate, AI will be able to solve all the problems in that domain. So then the challenge becomes, what can we simulate, right? It's easy to simulate a game of Go or chess, right? It's also, in some sense, easy to simulate programming. So that means programming will make a huge amount of progress. What we can't currently simulate is a cell. with all, I mean, like, you know, you can approximate lots of ways, but to actually model the entire complexity of a cell with all the different molecules that are in it, no one can do yet. Once we can simulate a cell or multiple cells, and then AI can start to infinitely many times optimize processes, create new proteins, all of medicine will be forever changed.
Very good. Thank you very much. Due to time, one or two quick short questions, then we'll go to our Q&A. John, next one to you. I wanted to ask you, what are NVIDIA's developments and business strategies related to non-traditional computing hardware, and how do these reflect their cooperation in this field?
Okay. Well, I'll touch on quantum since Q is here. So we are investing and looking potentially down the road as quantum as an opportunity for humanity. And it's an area where we're investing and collaborating actually with all the companies building quantum machines. And we feel that by providing the simulation, which is the early stages of where we expect to be in a few years, we're giving the foundation of technologies and ideas that we can work on.
Okay, very good. Kohei, for you, one follow-up. What forms of cooperation exist between leading HPC sites, and how do they impact the field? And this can be to anyone, actually, but I'd like to start with you.
What kind of collaboration that exists? I mean, you know, HPC people are collaborating around the world, so so we're all talking to each other.
Can you give me a specific example? Anyone on the table?
Well, you know,
I can talk a little bit about.
Okay.
We have actually existing relationships in Germany as well as in Japan that I can speak to specifically. But I wanted to mention, really, in this context of development of large language models for science, really an effort we have underway called the Trillion Parameter Consortium. We've got some 1,200 participants, if you will, from across the world really working together on a very active basis. They have conversations every couple of weeks, really sharing what it is they're up to and what it is they're learning, and also helping each other solve problems as they come up. And so it's a loose-knit coalition at this point in time. NVIDIA is a member, so we've got industry as well as academia. Jülich is a member as well, and so it's really exciting for us to see people come together as things are moving fastly. Very fast has been suggested here, and so really having the community and active discussion on a regular basis is really essential.
Great. And I wanted to conclude here. I know Astrid Lambrecht could not join us tonight, and I did have some questions that I prepared for her. So I'd like to ask one of the questions I prepared for her, and anyone here in the panel can answer it. The question for Ms. Lambrecht was, what is the potential of high-performance computing, HPCs, in Germany and across Europe? Of course, that is her area, but if maybe anyone would like to chime in on that. Maybe it would be good since you're here based, yeah?
Sure. I think Germany has partially missed the boat a little bit on some of the foundational models for natural language, for programming, for image generation, and things like that. But where Germany is really, really strong is actually in the sciences, the foundational sciences of physics, chemistry, biology. And we already brought this up, new kinds of batteries, new kinds of molecules, crystal structures, and so on will be developed by AI, and I think it would be phenomenal. I'm writing a whole book about this, trying to motivate other people because I can't do it myself right now, but it would be phenomenal for Germany to build a foundational model for reality, for science, for physics, chemistry, biology, train it all jointly, and lead the world in that.
Great, thank you. Anyone else on that?
Well, I was going to mention, since you mentioned not just Germany, but Europe,
yeah.
I think there is a lot of science going on in Europe and a lot of research. And then we have to give some credit to the European Union and the Euro HPC, which is now Euro AI almost, because they are investing in some large systems in Europe dedicated to research computing. You mentioned the Jülich system, and we have to give some credit. The Gauss Society in Germany has acquired some systems, so that's another thing. And I saw a shirt there with the Helmholtz and their work around life sciences research, which is something, again, NVIDIA, even though we're a company, we watch this, we collaborate with different institutes. Yeah. So we see that, and I think from our founder, CEO, it's a very important thing to support the science in Europe through systems, but also through a number of people. We have like 3,000 plus people in Europe, and a lot of them work directly with scientists around future technologies and future accomplishments.
Excellent. Thank you very much. Good. Then I would say for this portion, we have concluded. We're going to open up the floor now for Q&A. Back in the US, we use the expression KISS, not just ein Kuss, but keep it sweet and simple. So I would just ask you, you can introduce yourself, your affiliation if you wish to, and then directly the question. If it is to one of our panelists, you can be direct, and if not, just to the panel in general. I believe we have one or two people with a microphone. I see already the first hand here, so I'll give it to the gentleman there. And please, if you want to stand up and introduce yourself, and we'll look forward to your question.
I'm Alex from Jülich. I'm one of the people preparing the machine that will be the exascale machine in Jülich. You specifically mentioned...
you would be...
No, it was just...
.com? You.com or what you know?
The subject came up. You mentioned Llama 3.1 and Llama 4. Turns out that Meta already has a Llama 3.2, and we cannot use it in Europe because of the EU AI Act. The question for the panel is, have Europe shot itself on the foot with that?
Excellent.
Oh man, I have some strong opinions on that.
Good question. Would you like to, maybe since you're based here, you want to start on that?
It is so. I live in California now, but
okay,
still German and
yeah.
German citizen. It is so unfortunate that Europe has overregulated a whole ecosystem before it could even take off, and has especially painfully regulated the abstract model sizes and things like that. It makes no sense to regulate the number of parameters of a neural network. Right? You can use that neural network and put training data in to detect breast cancer or to put it into a drone and drop a hand grenade. Like the abstract model size has nothing to do with its applications. And so for the European Union to have regulated already model sizes just prevented any foundational model company from wanting to do business in Europe and train models in the whole ecosystem. Now, it does make sense to regulate applications of AI. I also don't want some self-driving car startup drive by me in the Autobahn with 100+ miles an hour without having gone through certification. I don't want an AI neurosurgeon to just practice in my brain to see if it works or not, right? It makes sense, but you regulate applications of the technology, and the way the European Union has regulated AI is a little bit akin to saying, sometimes there's illegal content on the internet, so how about we just provide only slow internet and smaller hard drives, so there's less illegal stuff on the internet.
Okay.
It just makes no sense.
No. Excellent. Anyone else on that one? I think it's a very good opinion. No? Then we'll move on to our next one. If we have a hand up, and if the person with the microphone sees it, I see a gentleman here, and please don't be shy with the questions. Right here in the front. Go ahead.
Good question.
I was curious about your opinions of allocation of compute for training and inference, and in this context, the role of ASICs.
Could we be a little more specific on the question? Because that's very broad.
So currently the main compute is allocated for training large language models, and as we see more applications of these systems, we see more inference compute becoming playing a larger role. And currently, few players who are designing specific chips for transformer architectures have been coming into play, and there is trade-offs between the latency and but dependency on the specific architecture and so on. So I was just wondering.
Excellent. And then just repeat the specific question would be?
So thoughts on the allocation of compute for training and inference in current and future states, and role of ASICs in this paradigm.
Good. Would anyone like to take a shot at that?
I don't want to dominate, but I guess you want to.
Anyone out here? No? Okay, then go ahead.
All right. So maybe just for other people to understand, so one of the big breakthroughs of the O1 model from OpenAI is, we don't know for sure, but very likely, the idea to spend more time at inference rather than at training. So you take the same model, but instead of just predicting every next token or every next word, you predict it, you have another model that asks, is this sensible? Does that make sense? And then if not, you say, predict it again. And you can basically go through 50,000 inference steps and predictions instead of just one. And it turns out, if you allow the model to do that and you have another model or maybe even the same model that gives feedback on the output, it will take longer, it's more inference compute, but it'll also be a lot more accurate and much better at logical reasoning because it catches its own mistakes that you kind of just throw out. And so the question here, I think, is how much more do we do inference at test or compute at test time? And I think the answer is probably a lot more if you really care about the accuracy. And what's nice is that it's very easy to tune, right? You just say, you allow more compute cycles for each answer. It takes longer, but you'll get more accurate answers. And then I think in terms of specific compute architectures for just transformers, I'm actually not a big believer in it. I've seen a lot of startups over the years pitch that idea. They say, oh, we're 100%, like 100x faster than an NVIDIA GPU. And I'm like, okay, how long is it going to take you to get this model out and into production and actually at scale and into a hyperscaler like AWS so I can really use it? And you have the whole infrastructure and programming and so on. And by the time, in 4 or 5 years later, that they're actually able to get this out, NVIDIA is also 100x faster than NVIDIA was 5 years earlier. So it's really hard to build these very specific pieces of hardware for startups.
Excellent. Good. Thank you very much. We have questions. I see right here in front of me. Anyone behind me too? Then we'll get to you also. Gentleman here.
Hello. Is it on? Hello.
Yes.
My name is Wilbert from Hamburg, ACG. My question is to all of you. What are you doing or what boundaries do you have to prevent this to come into the technology singularity? You know, when the machines start to develop themselves, or are you seeking that?
Ooh, consciousness of machines. Anyone, please, if you want to put your opinion on that one. John, go ahead. I see.
Well, I was going to say,
go ahead.
When we look at machines, we have specific roles for what we want things to accomplish. For example, if we want a robot to pick up a glass of water, we don't expect the same robot to be driving a car. So we need to put limits in what we want in certain areas, and those boundaries and guardrails are going to help us focus what we want to accomplish with specific technologies. So we have a robot, for example, to help us build a car or build a house or give us a glass of water. That's a different use case, and it has to be bound by different technologies and software and hardware.
John, who regulates those boundaries, or are they even able to be regulated?
Well, I mean, like, you know, Richard was mentioning, we have to look at the governments play a role, but the companies also play a role. But you have to do everything by thinking in the future and at what level you come in and so forth.
Okay.
You know, I mean, at our company, we think about everything we do and how it affects technologies and deployments, because we just think of it that way. It comes natural to us.
Okay, good. Anyone else on that one?
I mean, I feel like one of the few areas where you do want some regulation where I'm worried.
Just a quick closing statement, because I have 1 or 2 more questions. Go ahead, though, Richard. You're fine.
Where I'm worried about the singularity only is in biology and making sure that we don't allow all kinds of viral training data, as in like training data about viruses and bacteria. That is maybe the one space where I would be worried. And other than that, I'm all for the superintelligence and pretty much all other dimensions of intelligence.
Excellent. Good. We have a question behind me. I believe there's a gentleman there. If we have a microphone for him. And we have also there, you'll be next.
Thanks a lot, Mirko Rossini from Ulm University. Sort of queuing up to the first question, I wanted to ask some further comments from the panelists on the need or not of explainable AI models. So rather than like specific models, 1, 2 nodes and the depth, but like explainable models.
Could you, I'm not sure I quite understand the question. Could you specifically ask what area now?
As I understand it, there is a discussion about machine learning AI models to be explainable, meaning that you can ask them how they decide on some topic. And some models are, some models are not. So I wanted to ask what are the opinion if these are needed.
If they're necessary. Okay, now I understand the question.
Okay, maybe. So scientifically explainable high-performance computing, I think we're in Japan is trying to develop a flagship model that combines both fundamental simulation with AI. So it's a hybrid computing, and of course, you know, we also try to introduce quantum computing with it. So it's a combination that matters. So the fundamental computing that actually gives you the explainable solutions, but at the same time you have to use AI to accelerate your calculations. So that's the direction that the Japanese flagship computing is heading.
Thank you very much. I see we have about 4 or 5 minutes here. We have a question here, and then after that, we'll have time for one final question. Please.
Hi, Ingmar from the startup exascale. There's this neuroscience result that says that more intelligent people use their brain more efficiently, and it was also alluded to. So my question is, what do you think is the path to making more intelligent models for a fixed amount of flops?
Interesting.
Yep, I'll jump in here a little bit and start the conversation, but there's quite an effort underway really at looking at how we can make both learning and inference more efficient, really. And this can be done at different scales and different applications. And so I think both industry and academia and in our case, the government laboratories in the US are all working to achieve this. I think really key here is just being able to really kind of break things down and understand what's occurring and making sure that you've got good results, and then really kind of looking to scale that back up in terms of applications. So really important in that way, but a good effort underway. I think we're just beginning to explore this because the field is moving quickly. So,
absolutely. Anyone else on a final statement there? Then we'll open it up for a final Q&A. If I see one last hand, anyone behind me? Yes, here. The gentleman for the final question, please.
So I was wondering whether you had an interesting, open, fundamental scientific question about the workings of artificial intelligence. Say if you were a graduate student and needed to pick a topic to work on, what would that be these days? Are there any open questions of the fundamental kind and not in the application sense? So maybe for Richard or anyone else?
Sure. Richard, please.
So many. I think sample efficiency is somewhat connected also, like being able to learn with fewer samples, and it's both an algorithmic problem as well as potentially eventually a hardware problem. I think finding more energy efficient ways to implement a simple neuron should definitely exist, right? We know in the brain it exists. So in terms of hardware, there are a lot of interesting foundational questions. I think connecting simulations to foundational models. There's a lot there, especially for science. Personally, I'm very interested right now about the upper bounds of intelligence. And there's something called Kolmogorov complexity and Solomonov bounds that basically say that the complexity of, I don't know if I can answer that in a super short amount of time, but basically you can look at what's the most optimal prediction model that you can possibly build for any kind of sequence. And it's connected to a program, sort of information theory, algorithmic information theory, where if you can find a program that generated that sequence, you basically want to assign a lot of probability to that sequence. And so the simplest program is the most likely to have generated that sequence. And so there's some pretty fundamental theoretical questions in computer science about what is the absolute best prediction model. And other dimensions and groups of intelligence have their own bounds, and several of them eventually are based in physics, like how much can we perceive in the world. There's a deep connections to like the speed of light cone of the sensor that looks into things. And so there are all kinds of highly interesting theoretical lines of research that no one has yet explored.
Excellent. Thank you very much. Thank you all for the excellent questions. I see that we have the red for the timer, which means we have to wrap it up. So I've learned that it's a tradition here at our Falling Wall Science Summit for this final question to go through our panel. And that is, what is the next wall that you would like to tear down to help with the implementation and development of our field here, HPCs and AI solutions? I would ask that we limit it, thank you for the bell, to 2 or 3 sentences. Maybe we'll go this way. Paul, we'll start with you.
Yeah, I think as indicated by the conversation, really working together in a collaborative way, really sharing as we're learning and really valuing that, really to drive open science is really key.
Thank you. Kohei, please.
Introduction of quantum in the future.
Introduction of quantum. You make it sound so easy. Very good. Please, John.
I was going to say a little bit more. I think that collaboration is something we value very much in our company with scientific communities. They drive a lot of innovation. And then when you look at quantum, and we also think about energy efficiency. So there is all of this coming together. How do you drive energy efficiency? Richard touched on the last question we actually had, which was kind of almost leading to your question. I think energy efficiency, looking at optimizing software, and how do we all work together to accomplish the same results. We all want to try to fix weather and climate or understand it better, extreme weather phenomena. We all want to look at health and how do we make it easier. But how do you end up making it all much more efficient and at a much faster pace is the goal. And that will only come by collaboration, fast execution. I think he touched earlier, or we cannot be designing machines 5 years out. We have to look in front of us. Technology is moving too fast, and we need to, as humanity, to think of how do we, based on AI, how can we accelerate the discovery that we have to do in order to improve our world.
Excellent, thank you. Richard, the last word to you. Take a breath, we have an extra minute, no problem.
The future is already here, it's just not equally distributed. So I'm just very excited to get actually accurate answers at scale into many different organizations.
Fantastic, thank you. Ladies and gentlemen, please, a round of applause for our distinguished panel today. Thank you all very much.